Good morning, everyone. Today I will present our work titled Point to Dense Supervision Framework for SAM based remote sensing segmentation with prototype refinement and structure aware, confidence guided topology learning. This work addresses a fundamental problem in remote sensing: how to obtain accurate semantic segmentation when dense annotations are extremely limited. The key idea is simple yet powerful. We transform sparse point annotations into reliable dense mask by adapting a very famous foundational model, the segment anything model, and progressively refining pseudo labels using structural and semantic reasoning. You can see that remote sensing has grown rapidly due to the advances in satellite and aerial sensing platform. The datasets so captured support Earth observation applications like environmental monitoring, urban planning, agriculture, disaster management, to name a few. But all these applications depend on semantic understanding, meaning assigning a class label to every pixel, as we can see in figure 1, wherein every pixel has been assigned a color and each color indicates a specific class. The problem, however, is annotation cost. Dense pixel-wise labeling that to manually is expensive, time-consuming, error-prone, and cumbersome. So instead of dense labels, we often have weak annotations, say point annotations, but they are cheap, but they provide very little special information. This creates an ill-posed learning problem. The model must infer full object shapes from only a few labeled pixels. If we look at the different types of annotation, dense masks provide full supervision but are costly. Bounding boxes will give location but poor shape information. Scribble just gives some approximate structure. Point annotations are cheapest, just a few clicks per object, but contain minimal geometric information. Our work specifically targets point supervision as it represents the most scalable annotation strategy for Earth observation. Now, coming to the core idea of our work, we propose a mixed supervised pipeline. We assume that we have a small data set of dense mask, but we have a large data set with only point annotation, wherein each image has point annotated mask, which means that only some of the pixels have been assigned their specific classes. We have to learn a segmentation function for these images to get the complete dense annotated mask, enforcing point level consistency. The pipeline has 4 stages: adapt SAM to remote sensing images, generate pseudomask from the points, then refine this pseudomask using class prototypes and select the reliable masks for self training. So instead of trusting SAM directly, we iteratively improve supervision quality. The goal is not just segmentation, it is building reliable training labels automatically in the sequential process. So, going to the details, in the first step, that is SAM adaptation and pseudo label generation, we can see that segment anything model is usually trained on natural images. When it comes to remote sensing images, we have different viewpoints, different textures, different object scales. So direct application will lead to domain shift errors. Apart from that, the classical SAM has class agnostic semantic segmentation. Now, by class agnostic, we mean that it kind of gives boundaries but is independent of classes. Therefore, we have to perform limited supervised adaptation using the small dense data set. The encoder is mostly frozen to preserve general information, while selected layers are unfrozen to learn remote sensing semantics. Training uses a combined loss, supervised segmentation loss, and a topology loss enforcing boundary consistency. This topology loss ensures predicted boundaries align structurally with ground truth, very critical for land cover semantic segmentation. So after adaptation, SAM generates point conditioned pseudo mask for weakly labeled images while enforcing consistency with this provided points. Next, we have to refine this pseudo mask. So initial pseudo mask might still contain error, especially points that are far from the point prompts. To correct this, we introduce prototype refinement. So from the densely labeled images that we have, we build a prototype bank. This prototype is simply the average feature embedding of class inside SAM's feature space. So in the prototype bank, we have a prototype of each class. Now, we have the SAM predictions. We will identify uncertain pixels from this SAM using prediction entropy and boundary instability. Suppose in this part, it seems like the area has unstable boundary, so it might be having some uncertain pixels. Around these uncertain pixels, each of them, we create some patches. And these patches will have a prototype class will have a class. So this patch class will be matched to each of the prototypes, and then we measure the minimum distance between this prototype and the patch class. But we immediately do not assign the class prototype of the nearest prototype as in the prototype bank to this patch. What we do is, if the similarity between the patch class and the class prototype exceeds a confidence threshold, only then we correct this label. Otherwise, we keep the patch as belonging to the original class that it was predicted. So intuitively, SAM gives geometric intuition while prototypes provide semantic grounding. Next, we have to either select one of these predictions or merge it. So we go through a multi-strategy fusion of pseudomask. The original SAM mask is there, the prototype refined mask is there. Each will capture different strengths. So instead of averaging, we perform a confidence-based fusion. A reliability score will be evaluated using prediction entropy, spatial consistency, and boundary regularity. The mask with the highest structural confidence will be selected as the fused prediction. Now, these fused predictions will be there for each of the weakly labeled image. But we cannot add or augment all to the dense label set because it might introduce errors in retraining of the model. So we have to find the most confident predictions. We do that by computing a final confidence score combining semantic correctness and geometric quality, and only the most confident masks are added to the dense label training set. Finally, the model will be retrained using the unified loss and the merged set of images and labels. We evaluate our work on two benchmark dataset DLRST, wherein only 170 images out of 2100 have been used as dense label, remaining all are sparse annotations. Similarly, for Deep Globe, we use just 98 images as dense mask. In the results, in the ablation, we can show that each component contributes progressively. And in the performance comparison, we can see that our proposed model has outperformed both classical point supervised as well as recent SAM based methods. This demonstrates that reliable pseudo label refinement is more important than simply using a foundation model. Similarly, through the qualitative analysis, we can see that our proposed model is closest to the ground truth. To conclude, we present a framework that converts sparse point annotation into reliable dense supervision. The method reduces dependency on expensive dense annotation while maintaining strong segmentation performances. And also, This provides a scalable direction for large scale geospatial mapping where annotation cost is the main bottleneck. Thank you.